What we're going to do today is called percent composition and then combustion analysis. Your test still has to be done eventually, but here we go. Percent composition. You already did homework on this, right? It's super not that bad, but let's make sure you can do it. One can find the percent mass of a compound that comes from each of the elements in the compound by using this equation. The percent of the element is the number of atoms times the atomic weight divided by the formula weight of the compound. In the shortest nutshell of all time, because we spent a lot of time more on something that we don't usually do. If we have CO2, to find the percent of oxygen, you take the mass, technically it said the number of atoms, 2, times the mass of the thing, which oxygen is 16. All right, and you divide it by the total mass of this substance. CO2 ends up to be 44. So you end up, and you're going to multiply it by 100. So you end up with 32 divided by 44, or 16/22, or 8/11. I don't know that answer. Someone? Then you multiply it by 100. You're going to need a calculator all day long today. .7272. All right, so it was on the previous slide. 1 second. 72.7%. It's right here. All right, now you could do math for the other one, and you could take it's 12 over 44, or it's just 100 minus 72%, and that's the other percentage. Easy enough? Okay, I'm not going to spend much more time on that because that's pretty simple. All right, there's whatever. This is the one that's closest to the exam. What is the percent copper in copper 2 oxide? Copper 2 oxide happens to be CuO. So it's just 63 over 79.5. It's very similar to the one on the exam. Okay, next. All right, so more of that. All right, moles we already said is a big number, right? Okay, we're going to move on fast. Avogadro's number we already talked about. Molar mass we've already talked about. Yes.
I'm here. I'm just writing my essay, Nelson.
Okay. Okay. All right. So this will be the first thing we'll focus a lot on today, and that's called finding the empirical formulas, which you already also should have done homework on by now. And hopefully it wasn't the hardest thing that we've had to do. Finding an empirical formula just involves a little bit of math given the percent of things. So it's the reverse of what we just did. So first off, an empirical formula, for your information, is the lowest ratio of elements. So like an empirical for water would be H2O because it's 2 to 1. I can't reduce those. Sugar, though, is C6H12O6, correct? That is not an empirical formula. That's the molecular formula. That's what it is, but its empirical formula would be CH2O because we put it in the lowest ratio of terms. All right? So that's what we're going to do today is find an empirical formula through just some math when we're given percentages. This is on your exam. On the level of difficulty, it's a 1 compared to what we've been doing, which has been like a 6 or a 7. So here we go. All right, to calculate the empirical formula, I'm just going to talk this quick. You'll go percent of your elements, and we're going to make an assumption. And it's a super nice assumption. If I tell you something is 40% carbon, well then if we just say, all right, I have 100 grams of the thing, then I know it's 40 grams of carbon. Does that make sense? So every time we do this, we make one assumption, and that's that our sample is 100 grams. And really, all that is doing is taking our percent sign and changing it to a gram. Because once I have it in grams, I can make it moles. And once I can have moles, I can find the ratio of moles, and that will tell me the empirical formula. It's actually genius, whoever did this. All right? So, 100 grams, convert to moles. Then once you have moles, you can calculate the mole ratio. Pretty not that bad. Let's do an example here. So this is the stuff in your sunscreen. It says the compound para-amino-benzoic acid, or PABA. If you buy sunscreen, you should check that it has PABA. That's the only way you know that it is actually very good. Is composed of carbon, hydrogen, nitrogen, and oxygen. Find the empirical formula for PABA. So this is what we would do. We first assume it's 100 grams. So that really just converts all these percents to grams, right? So if I was writing a step-by-step thing, I would just write change percent to grams. That would be my first step. Now, I'm going to do this in a big, long vertical slide. However you do it in your notes is up to you, but make sure you understand what we're doing each time we do it. All right, so I'm going to write these down here. I'm going to put 61.31 grams of carbon. Then underneath that, 5.14 grams of hydrogen. Underneath that is 10.21, and that would be nitrogen. And then I already lost it. 23.33 of oxygen. All right, now, is anyone offended by how I wrote H, N, and O? Okay, they are diatomic, correct? But they are not here. Because we're finding the parts of them in a compound. This is not a reaction, right? We're just going to say that this has a formula. Oops. We know that it's made C, H, O, and N. We're finding the numbers right there. Yeah, there you are, bio people. You're like, whoa, John. All right. We're finding those numbers. So in this instance, we do not consider them to be diatomic because they are not a molecule. They are part of PABA. All right. So here we go. So the first step, you just write them all out. This is so ugly. And then the next step, are we ready? If you're writing notes, the next step would be to divide each one by their molar mass. Divide each element by its molar mass. All right, and we get these straight from the periodic table. I'm going to round, which you should not do, but I'm going to. But you shouldn't. I'm a good teacher. Carbon's 12, hydrogen's 1, nitrogen's 14, and oxygen is 16. Then I need people calculating. Someone start at the bottom, someone in the middle, someone somewhere else. Let's get these four numbers pretty quick. I'll do hydrogen. I got it. Nitrogen's what? 0.73. Okay. I'll do carbon. Okay. Now, are you with me on the two steps? Write them as grams, divide by their molar mass. Most kids love these problems, by the way, because you just do step 1, step 2, step 3, and then miraculously crap works. All right, step 3, are you ready? Step 3 is to divide all of these answers by the smallest of the answers. divide all of the answers by the smallest answer, which is 0.73, right? All right. Well, this one's a 2.
I'll do hydrogen.
You'll do hydrogen?
Yeah, just one.
No.
No, not
Nitrogen?
Nitrogen, that's what.
Good. Thank you for doing that. I was confused too. All right. This is a 5, 6, or 7-ish?
That's like a 7.04.
7.04? All right. I'll put 7.04, but we're just going to call it a 7. If we didn't round, I'll tell you it'd be like 7.00 something. All right? And this is obviously going to be a 7.04 also. If, and it's not a big if, most of the time this if is a yes. If they're all really close to a whole number, then you're pretty much done. Now, if they're not, it gets more complicated. But 7.04 is pretty much 7, right? So let's erase these. So the final step is just to write how it goes. There are 7 C's, 7 H's, 1 N, 2 O's. Thank you. C7H7NO2. That is your empirical formula for PABA. Okay? You should list them how it is given to you in this exact order as given. In this one, you don't know this yet, but you wouldn't put H first too because it's more than 3.
They don't come out almost like in number.
All right.
Number.
So I'll show you, yeah. What you do, let's say we did the math, and this was a 7.25. 0.25. You just kind of got to use your math brain and say, how can a 0.25 become a 1? You multiply it by 4. So every one of these would be 4. So it would suck. It would be C28, H28, oh, what do we say, 816. Yeah, it would. Thank you. When you take that, yes, to make it a 1, we multiply it by 4. Multiply that by 4, it is 29. Thank you. And I screwed up here too. But that is the idea. Now, when that happens, they only really do it to you when it's either a 0.5, so you just double everything, or a 0.33, and then you just triple everything. It never is like a 0.1, and you have to multiply everything by 10. Oh, hey, that's cute. Okay. Now, we didn't write out the final step, but the final step would be to take your whole numbers and make them part of the formula. I don't know. Good enough? Where's another one? Here you go. Do this one on your own. Let's take about 3 minutes. Someone make sure on. All right, we all decided that this turned out to be SO2. And this was equal to its empirical formula. Let's read the second part. It says the molecular weight for this compound is 64.07. What is the molecular formula? So this is what you do. The empirical formula is the lowest ratio. The molecular formula is the true ratio. So what you would do to figure this out is you find the mass of this thing. All right, this is 32 plus 32. What is the mass of it then? 64. All right, the mass of the empirical formula is 64. What does this say? 64, right? Those are the same value. So in this problem, we would say that the empirical formula is the same as the molecular formula. Now, when it is not, it would be something like this. It would say that the molecular weight for this compound is 128. And so what you would do there is you would find the mass of this, and you would take the molecular formula and divide it by that. 128 divided by 64 would be 2. And that 2 would mean you have to double everything. So it would be S2O4. Who understood that part? Okay. Almost everyone on a real test will ask the empirical formula, then give you a molecular weight, and then ask what the molecular formula is. Once in a while they're the same, but usually they are not. What, is this the one we already did? Okay. All right. Vitamin C contains 3 elements, C, H, and O. There are your numbers. We want the empirical, then at the bottom in bold, the molar mass of vitamin C is 1.76. What is the molecular formula? All right, remind me this time for real to unpause it. Thank you. All right, so just as quick as I can, we took 40.9 and divided by 12, right? 4.58 divided by 1, 54.5 and divided by 16. What did we get for carbon? What's that? 3.41?
Yes.
That's ugly. Oh wait, we're not to that part yet. I'm sorry. 4.5. And what was this one? All right. And then we divide 3.41, 3.41, 3.41. That's a 1, and then you say 1.3. I'm just going to say 1.33. All right. So if they're not whole numbers, you have to make them all whole numbers. Multiply by 3, 3, 3. So we get 3, 4, and 3, right? So C3H4O3. Who had that much? All right. So the next step then is to find what this mass would be. So this is the empirical formula. But does it match that? So this is 30, 40, 80 something, 84? 88. All right, so this is 88. But the real mass is this. So, I mean, you all know it, but 176, you would go through this process, divided by 88. That's just 2, correct? So vitamin C would then be all of this doubled. So vitamin C is C6H8O6. Who had that right?
How do we get to there?
That's all right. We take the mass it should be, and we divide it by the mass that it is, and that would give me a whole number, and it gave me the number 2. That means that every one of these should be multiplied by 2.
Wait, so we got the 88.
From 3 C's,
Okay.
that's 36,
That's nice.
then 40, then plus 48. Okay, who, once again, who had C6H8O6? Okay, then if you can do that problem, you can do the one on the test. The test is in a couple of days. Don't forget it. Like, this one's supposed to be the softball. Well, it's not a softball, but it's not nearly as hard as limiting reactants, right? Can we all agree on that? All right. Now let's make it harder. Now, anytime you're like, man, this class sucks, remember who it was that bubbled in the 3 bubbles it took for you to register for this class. It wasn't me. It was you. So here we go. Combustion analysis. We're going to use combustion analysis to do the exact same thing. Oh yeah, it's not on paper anymore, is it? Sorry. What? Literal pants? It's digital registration. Sorry, people watching this video. All right. So here's the deal. We're going to find an organic molecule, which means it's CH and O's, right, and N's sometimes. And we don't know what it is. So when you don't know what something is, burn it and see what happens. And that's literally what combustion analysis is. Compounds containing C, H, and O are routinely analyzed through combustion in a chamber like this. So they burn it. Oh boy, what if you're watching this? You just probably had a spasm. They burn it, and then they send it through this to purify it, and then they have a thing that absorbs water and a thing that absorbs the carbon dioxide produced. And let me show you something. It's pretty, whoops, wrong one still. It's pretty cool. If we don't know what we have, but we know it came from, let's just say, a CH plus an O2, number, right? We don't know them. But it makes H2O and CO2. Sorry to reverse the order. It doesn't matter. But let's think about this. The amount of water produced is dependent on the amount of H's that was present in the CH thing, right? And the amount of carbon dioxide produced is dependent on the amount of carbon that was there in the first place. What? Not yet. In this, we're not going to balance reactions. But in an overall reaction, yes. So, are we all right with that idea that the water and the carbon dioxide produced are dependent on the thing? So look, if I can light this stuff on fire, and I can use math to figure out the amount of just H and the amount of just C, then I can do what we've just been doing. Because I'm going to solve for grams of C, grams for H, divide it by 12, divide it by 1, and that will give me the molar thing, the smaller answer, divide it by both. That gives me a ratio, and I'm on fire because I was burned. All right? So... whoops. So C is determined from the mass of CO2 produced. H is determined from the mass of H2O produced. And O is determined by the difference after the C and H have been determined. We can't just do O math just straight up, because remember, to burn it, we also had excess oxygen. But if we know the mass of C, and we know the mass of H, and we know the mass of C, H, and O, then we can use this to calculate the mass of O that's left over. That was only the O that was part of the CHO. All right, so it's just a couple more steps that we add before we do what we've been doing. So let's attack it. The only way to do good in chemistry is to practice. Oh, I'm out. I have a whole different slide show for combustion analysis. 51 slides. That's a good slide, right? Hey, this week in AP Chemistry in 2014, we did those things. All right. Thank you for checking, though. All right, here, Bryson will like this. Step 1, convert mass of CO2 to moles of C. Step 2, convert mass of H2O to moles of H. Step 3, divide by the smallest answer. Step 4, write the formula. Yep. All right, so here we go. A sample of a simple hydrocarbon undergoes complete combustion to produce 4.4 grams of CO2 and 2.7 grams of H2O. What is the empirical formula of this compound? All right. So step number 1 told us to do what that we just wrote down? All right, convert the mass of CO2 to moles of what? Moles of carbon. So my picket fence is too long. Definitely doesn't need to be this long. All right, my picket fence, I will start with my mass of CO2, 4.4 grams of CO2. All right, what must go down on the bottom right? Grams of CO2. And that's always, if we're writing grams, it's always per what? 1 mole of CO2. And if you add the mass of 1 C and 2 O's, it's 44 grams. Every time. All right, now, this next part, once in a while a kid gets really baffled what I'm about to do. But we're going to, well, what goes down here? All right, mole CO2. What am I trying to answer again? What's that? Moles of carbon, right? All right, so look, we are not looking at a balanced reaction, and usually that's where we find what goes here, correct? We're now looking at a formula. For every 1 CO2, how many C's are there? 1. So far, not that bad. All right, so for every 1 CO2, I have 1 mole of carbon. All right, so 4.4 divided by 44.1, right? That's a number that will be important. The next step would be what? All right, convert water to moles of H, correct? How many grams of water? 2.7. All right, 18 grams of H2O. 1 mole H2O. What must go down there? And for every 1 mole of H2O, how many H's do I have?
2.
I don't need that. Pick it right there. I think I just did it, didn't I? Whatever. Oh well. I have 2 mole of H. Now don't put 2 mole of H2. It's 1 mole of H, and we're solid. This didn't need to exist. All right, and then I do the math here. 2.7 times 2 divided by 18. 0.3 mole of H. What was the next step in our set of rules? Divide by the smallest answer. So it's 0.1. So I end up with this being a 3, this being a 1, right? So what is the empirical formula of this thing I'm talking about? CH3. Now, CH3 isn't a thing, but that's an empirical formula of C2H6, which is a thing. But we wouldn't know that because I didn't give you a mass, right? I could, and I do on the test. What's the mass of CH3? 15 grams, right? So what if I told you that the real mass of this was 75 grams? You would take 75, divide it by 15, and then you multiply everything by 5, right? Okay, now, this was the very, very, very most basic combustion analysis, and they're never this easy, because that's just the crappy world we live in. If there's no O, they're extremely easy. Who thought that was pretty easy? Follow 4 steps and you have an answer. And that only works if there's not an oxygen. It's more complicated if you have an oxygen. Because if there is oxygen, we have to find the grams of C, grams of H, grams of O. So it's more complicated. So, sample of hydrocarbons. So this is just C's and H's again. All right, so what if there's more? If there's more, you must first find the number of grams of both carbon and hydrogen from the moles of both you just started with. Then you add those and subtract from the original mass. The difference is the mass of the oxygen present. Then you have to divide it by the mass of oxygen to get moles. Once you have moles, you divide all by their lowest answer, and then you're off to the races again. Now, that was a lot of words, like a lot of words, but we can do it. So here we go. To review, you find the moles of carbon from carbon dioxide, or you divide by 45 or 44. All right? And this is, if this is just C's and H's, well, it works fine too. Number 2, you find the moles of hydrogen from water by dividing by 9. Now, what do I mean? Like, we just did a picket fence to do this, didn't we? This process always deals with carbon, always deals with hydrogen. So I'll come back to this, don't worry. But look at this picket fence. Every single time in this picket fence, it's grams divided by 45 times 1 mole over 1 mole, right? And this is grams divided by 18, always multiplied by 2 over 1 mole. Or 2 over 18 is 9, right? So to save yourself some time in this, you can just strictly take CO2 and divide it by 44, and that's your moles. Take your water, divide it by 9, and that's your moles. It works every single time. All right, next, coming back to this. Number 3, convert both to grams and add together. This is if it has oxygen. If it didn't have oxygen, you'd really be done pretty much after 2. Because after 2, you would have your numbers divided by the lowest answer, convert it to a formula. Step 4, subtract your answer to number 3 from the original mass of the unknown hydrocarbon to find the mass of oxygen. I wish we had 10 more minutes in this class, not 3. Number 5, convert your mass of oxygen to moles of oxygen. 6, take all the moles you now have and divide each by the one with the smallest value. This is like running a race, and all of this is the uphill, and then when you get here, that's the downhill. You're like, I can do this part all day, all right? Because dividing by that and finding that is actually somewhat enjoyable. If these are whole numbers, then they are your subscripts on your hydrocarbon. If not, then multiply all by whatever number, that's probably one word, whatever, you need to make them all whole numbers. A lot of steps, right? I tried to write them out as specific as possible. You are welcome. Now, for these 2 girls that are gone, I've recorded today, and we'll upload this to YouTube if you need to watch anything. My YouTube channel is just my name. There's like 50 Tom Davidsons, though, so find the one that has my face attached to my name, too. Not the swimmer. Actually, diver, not a swimmer. He's much better looking than I am.
Nobody wants it to be just. It can't be nice in this world. Be a grumpy old man.
All right.
Mr. Davidson.
I am. The test is Thursday, so make sure you guys are ready. Do these homework problems there. All right, so let's go ahead and work on this practice problem real fast. This wasn't in class, but it'll help anyway. And we'll just follow these steps. So you have your 0.25 gram sample, and it's known to contain hydrogen and oxygen and carbon. So we have to do all of the big steps. So once again, the first step is find the moles of carbon dioxide by dividing by 44. So let me get the marker tool. We're going to take this and just divide it by 44. And I'll do that in just a second in my calculator. And we're going to find the moles of hydrogen by dividing by 9. Whoops, that was the wrong one. You probably knew that already. Sorry. I'm going to divide this by 44 and divide this by 9. And if you wonder, like, where on earth are those things coming from? It's coming from the picket fence. And we're saying, we're just trying to save time. And I'm saying, hey, if I have grams of water, I will always have 18 grams of water per 1 mole. That's H2O. And then in H2O, I will always have 1 mole H2O for every 2 moles of H. All right, and so 2 divided by 9, or it's divided by, sorry, let me just, 18, I just screwed this entire thing up, didn't I? It's right here. I am sorry. Okay, I'm sorry, whatever. 2 over 18 reduces to 1 over 9. And that's why in that one step in our instructions we said, hey, just take your grams of water, 0.15, and divide them by 9, because that's really all you're doing in the long run. All right, and the same was for carbon, the 44. I don't know why this is jumping so bad, but whatever. You just take that and divide it by 44. So let me pause it and we'll write these. All right, so you can see right here, we have our moles of carbon and our moles of hydrogen. All right, step 3 from the instructions, we said convert both to grams and add together. So this is going to be sort of annoying, but we're going to now take these back to grams. In order to get these back to grams, we really just go and do another short periodic, or not periodic table, picket fence. So we take our moles, and it's going to be ugly, but I'm going to squeeze them right here. I have moles of carbon, and for every 1 mole of carbon, I have 12 grams. So I just take this, multiply it by 12. I wrote C right here, but this is an H. And for hydrogen, this is pretty easy. For every 1 mole of hydrogen, I have 1 gram. So we do that math real quick. The one's easy, the other one I'll do in a second. All right, so when you do the math, take 0.0083 and you multiply it by 12, you get this. And that's your grams of carbon. You do the same, it's just 1, so that's easy. That's your grams of hydrogen. All right, and then I went ahead and added them together. Now we need to know this total because if we know the mass that we started with, oh, we're in trouble. All right, you may have already noticed this, but when I did this right here, I just didn't look at my calculator right. It's 0.0167, so this won't be the right answer. I apologize. So we have 0.0996, 0.0167, and I add those, and that works. We now get 0.1163. All right, so we'll take the sample that we started with. It was 0.2500. We're going to subtract the carbon and the hydrogen out, 0.1163, and we'll get that answer. All right, and that answer will be equal to 0.1337, and that will be the grams of O2. So now, and I know this gets ugly, but now we have the grams of O2, and up here we had the moles of carbon the moles of hydrogen. Remember, that's 0.0167 though. All right. So what I need to do next is I divide this by 32 to get the moles of oxygen. So let me go ahead and do that. And that's 0.0042. All right, so I have that value, I have that value, and I have this value. And now when I have them all in moles, this is the step where we just divide each one by the smallest value that's left in the or that is in the moles. And that will be the oxygen. So let's look right here. We take this and divide it by 0.0042, and that equals a 1. Take this, 0.0042, and that equals a 4. Take this, and that will equal a 2. So now we would know carbon, C2, then hydrogen, we just said was a 4, and then O. C2H4O. All right, I know that that was a lot, but hopefully that example helps reinforce the steps that we did and had you write down the page before. We're in the 3.5-ish range.